So today we are going to look at a new function. The function is used to model a finite force that's being applied over a very short period of time. So almost like a slap. Um, and so we want to be careful though, because we don't want to have an infinite amount of force over that short amount of time. So how are we going to do such a model? Well, we can start by taking a look at uh, that's fine. We can go ahead and use a red axes here. Let's center our axes about the origin initially, and my function is going to have a certain height from time minus tau to tau, and the idea is that the integral should be equal to 1. So I want to have that make this area be equal to 1. Okay, so therefore the height must be 1 over 2 tau. Okay, and so I'm going to call this function d sub, so d, oh, what's going on here? D sub tau of t is going to take on the value 1 over 2 tau for t in the interval from minus tau to tau, 0 elsewhere. Okay, and so again we built this function so that the integral from minus infinity to infinity of d sub tau of t is always equal to 1. Right? Okay, so now we're ready to define our new function, the Dirac delta function. So the Dirac delta function. The Dirac delta function is going to be the limit as tau goes to 0 of d sub tau of t. Now, what is that going to be? If we take a look at our picture over here, this is 1 tau, right? If I make tau a little bit smaller, what's going to happen? If I take tau to go to 0, then it's going to make a bigger and bigger height here, right? And so if we want to think about this in some intuitive terms, we might think about this as being infinity if t equals 0, 0 elsewhere. Now I put this in quotation marks because this is really not the way you would define a function, right? So we call this this is actually something called a generalized function. We're not going to get too deep into that, but this function that we're defining, or this generalized function that we're defining, has some very interesting properties. Before we get into the properties of the Dirac delta function, let's normally we don't take the Dirac function at 0. Normally we will shift the Dirac delta function off. So therefore we can say that the Dirac delta function of t minus c, right, is going to be equal to infinity if t equals c and then 0 elsewhere. And so this is going to be modeling a smack, a hit at time c. Okay, so let's take a look at some properties of this weird function. So first off, let us take a look at the limit, or the integral, before we do any limits. Delta of t minus c dt is equal to the limit as tau goes to 0, minus infinity to infinity. I'm pulling the limit out already. Okay, but you'll remember that this quantity, this d sub tau here, was built so that the integral was always equal to 1. And so that's going to be the limit as tau goes to 0 of 1, which is 1. And so this is another weird thing about this function, is that even though it has no width, the integral is actually equal to 1. Um, Furthermore, so this is one important property here. Another important property about the Dirac delta function is the following. If I take the Dirac delta function and I multiply it by a function of t, then notice that because the Dirac delta function is 0 everywhere except times c, the only piece of f of t that is going to matter is f of c. And so another way to rewrite this expression then is just as the Dirac delta function times f of c. And the important thing to notice here is that this is now a constant. Okay, let me rewrite that so it looks better here. This is delta of t minus c times f of c. Good. Now, the reason I wanted to write that is because we are next going to take the Laplace transform of the Dirac delta function. So that will be the integral from 0 to infinity e to the minus st Dirac t minus c dt. And what did we say about that? That's the same thing as taking the integral from 0 to infinity e to the minus cs times the Dirac of c dt. And this is now a constant that I can just pull out. And then what's the integral of the Dirac delta function? That's equal to 1. So therefore, we have the Laplace transform of the Dirac delta function is equal to just e to the minus cs. Good. All right. Now I think we are ready to... So by the way, what is the Laplace transform then of the delta function t minus c of f times f of t? You see what's going to happen? All that's going to happen is that this is going to just tack on the f of c, right? Good. All right. And so now let's have some fun here with this Laplace transform. And let's see, big question. Is there a function whose derivative is the Heaviside function? What would that mean? Well, that would say that y prime of t is equal to the Dirac delta function. Right? And just for the sake of making my algebra work out nicely, I'll take y of 0 to be 0. Okay, and so now go ahead and solve this using the Laplace transform. And we have s times y equals e to the minus cs. So y is equal to e to the minus cs over s. And so what is y of t then? Remember, y of t is just going to be equal to u sub c of t. So this says that the derivative of the Heaviside function is the Dirac delta function. The derivative of u sub c of t is delta. That's kind of weird, but it does make sense, right? Because what does the Heaviside function look like? 0 here, 0 here, and right at c, right, we have this vertical line here, and so the Dirac delta function is going to be 0 there, 0 there, and infinity here. So in some sense it does actually make sense that that would work. Although I should really emphasize here, right, that this function is not differentiable in the usual sense. Okay, so when we talk about differentiability here, we're talking about a generalized differentiability that we haven't really discussed before. Okay, so In the next video, we'll look at using the Dirac delta function in some differential equations.